Okay, now we have previously looked at the notion of systems on chip, and increasingly what we find nowadays is that there are so-called FPGA SoC architectures. An FPGA is a field programmable gate array, which basically means an array of gates that can be programmed to implement any kind of digital logic. An SoC is a system on chip where you basically have a CPU along with a number of different peripherals. So what does it mean to have an FPGA SoC? The idea is that you sort of try and get the best of both worlds, right? So the SoC by itself integrates the processor, some amount of memory, certain peripherals and custom logic on a single chip. And what an FPGA SoC does is it basically says it will take a hard processor system, in the sense that hard processor, the hard over here refers to the fact that it's a so-called hard macro. It is an actual piece of silicon that is configured to work exactly as a processor. It is not a soft macro in the sense that it's not given to you as a piece of Verilog or VHDL code that can get synthesized and put on the FPGA. There is actually a so-called hard IP. There is a block sitting on the silicon that can only perform this SoC functionality and cannot be reprogrammed as such to do something else. Okay, so that is the sense in which this word hard is used over here. Now the interesting thing is you have this processor system and you have the programmable logic, which is what's called the fabric, right, which is something that can be sort of modified or programmed to do any kind of logic implementation that you want. Now in some sense this is giving you the best of both worlds, right? It gives you a certain amount of hardware software co-design flexibility. You have an SoC, therefore you can pretty much get your entire problem solved by just writing software to start with, and then you can sort of figure out which components of that are slow or problematic and which ones do you want to implement in hardware, maybe to get better performance, or it could be to get lower power consumption, right? Because there might be certain things, let's say like it could be even an image processing accelerator that you want to do on the FPGA fabric, right? And you can do it directly on the same chip rather than adding on a separate chip onto your board, which both reduces the system cost and also reduces the power consumption. It also means that this processor system and the programmable logic can have extremely high bandwidth communication because they are on the same chip and they share wires essentially, right? And because of the fact that even the logic over here is programmable, it means that we can update both the hardware as well as the software after you have deployed it and actually released it as a product, right? So this is a sort of natural evolution, right? It started off, FPGAs originally started off as pure programmable logic, but then eventually it was, as we have discussed throughout this course, you don't just work with pure digital logic at some level, you want to get programmable solutions. Programmable hardware is difficult to do, so instead can you get something which also has a software component into it, right? And that's where essentially the integrated SoC based solutions have come in. There are a number of commercial FPGA SoCs that exist today, right? The more common ones are the Xilinx Zynq and the Zynq Ultra Scale and Ultra Scale Plus families. They are usually referred to as MP-SoCs, multi-processing systems on chip, right? The most common sort of combinations these days are typically something like a quad-core A53 or something in the A series of ARM, and also something from the R series, which is the sort of the high reliability or real-time versions of the processors. Most of them tend to also integrate a graphics processing unit. These are similar to the ones usually found in phones, right? They are tied very closely to the ARM processor, and in many cases they have a dedicated video codec. So effectively that ARM processor that's inside the FPGA is a fairly powerful processor. It's similar to what you would have in at least a mid-range phone today. But at the same time, it also has programmable logic with DSP slices. What do the DSP slices do? They are capable of high speed and high performance multiplication and addition, right? So this is a very powerful sort of combination that we have here. But of course Xilinx is not the only company that makes them. Altera, which was briefly a part of Intel, not briefly, for several years a part of Intel, but is now once again a separate company. they have their own Cyclone area and Stratix series, right, which once again have ARM Cortex processors, right. In some of them they are A9, the others have maybe more advanced processors. All of these also, just like the Xilinx series, they also have the DSP or the multiplier units. They also have like hardened memory controllers. Typically the word hardened in this context refers to the fact that there are actual physical memory controllers directly on the chip, right, and you do not have to write Verilog code to implement, let us say, a DRAM controller or something like that. Now there is another company called Microchip that makes what's called the PolarFire SoCs, right. These are interesting in the sense that they are going with RISC-V rather than ARM, and they also have what they call deterministic processors, which are sort of probably more suited towards real-time applications, right, and they're capable of running Linux and are also targeted at fairly low power consumption. So the point is that you have sort of a variety of different options to choose from, right, but the basic idea remains the same. You have a programmable processor and you have a certain amount of logic that can then be attached to it. So what do you do with this logic, right? We basically want to have some way by which the processor and that FPGA can communicate with each other, right? And the way that the terminology, well, this is primarily Xilinx terminology, but it also applies in other contexts, is usually what's called the PS or the processing system, which is the ARM or the hardened SoC part of the chip, versus the PL, which is the programmable logic, right? Both of these need to sort of communicate well with each other. The communication, the most common sort of bus interface these days is the AXI bus, right? As we mentioned, ARM essentially led this whole definition of the AXI protocols, and these have got very nicely standardized, and most, in fact, IP blocks that are being designed these days are designed to be AXI compatible. Now it has sort of become a self-reinforcing virtuous circle, as they say, right, which basically means that you have this industry standard protocol. The good thing about it is it's an open protocol, so anybody can design an AXI compatible peripheral, which also has like very good capabilities, starting from very simple AXI Lite to high performance or even streaming data, right, and anybody can pretty much design their own peripherals as long as they are compatible with the AXI protocol. It means that you have the ability to tie them in to these systems, right, and actually have them communicate with the SoCs that exist. You can have various different kinds of interfaces. The memory mapped peripherals is the primary one that we focused on while talking about how to communicate between the CPU and a peripheral. But there are also so-called streaming interfaces where you can essentially have continuous data flow without having to give an address for each new data that you are trying to send. There are a number of common interface components including DMA controllers, bridges, memory controllers, and so on. All of these help to sort of manage the communication between the PL part and the PS part. So the common structure where this kind of thing is used is in the notion of what's called a hardware accelerator, right. So what does a hardware accelerator do? The idea is that you already have a CPU that's running some software, and you have sort of identified some function or some functionality within that software that is running too slow when you run it on the CPU. So what you would like to have is build a custom piece of digital logic, right, that can perform this computation. Now presumably, unless it's an extremely simple piece of computation, it's going to require you to maybe pull in some new data, perform some computations, and will most likely have some fairly complex processing engine or some finite state machine based control, right. So that's going to run inside your accelerator block. Now the CPU, rather than performing all the computations over here, its job has now been reduced to just configuring the block by writing certain control registers, giving a start signal, waiting for the data to get processed, right, and then either it gets back an interrupt or it keeps polling, right, checking a particular status signal in order to see whether the accelerator is done, right. Typically interrupts obviously are much more efficient because the CPU can actually do some other work in the meantime, or possibly even go to sleep if it just wants to save power. The point of course for this to work is that the accelerator also must have access to memory, which brings us back to our shared bus, our arbiters, our DMA controllers and so on, about how accelerators can access memory and get data back in order to perform computations. So this structure is a very common use or a common use case why FPGA SoCs are actually used in practice. Right? Now there are many different models that can be used for building these kind of acceleration systems, right. One is what is called the offload engine. So the word accelerator is a little confusing at times, right. It's not an accelerator is used primarily in the sense that it sort of speeds up computation, okay. But well, the primary thing it's doing is a so-called offload. What it's doing is it's just basically taking something that could have otherwise been done by the processor, but now the processor just configures the accelerator and initiates operation, and the offload engine then takes care of performing the computation. There could be scenarios where you have something that is much more tightly coupled with the processor. For example, for a long time there were processors that did not have built-in floating point units. Instead, they would have a different IP module or sometimes even a different chip that would be able to perform floating point computations alone, right? And that would act as a coprocessor. Effectively, whenever the CPU recognizes that it has this coprocessor attached and it finds that certain kinds of computations are required, it will send those instructions to the coprocessor and get the results back from them. But clearly that requires a very tight coupling so that the processor can literally look at instruction to instruction and decide whether the coprocessor should handle a given instruction or not. You might also have something which is sort of even more sort of isolated than the offload engine, where it is effectively some kind of a complete standalone engine that requires very minimal processor interaction in order to work. Although those are almost like separate independent processors, the most common model would be something like an offload engine. Now when you are designing these kind of accelerators, there are a number of different things you need to keep in mind, right? Clearly there is a lot of data that needs to move either from memory or from the CPU into the accelerator. This can and very often does become the bottleneck. You need to decide on partitioning. What is going to run in your CPU versus what's going to run in the accelerator, which is basically hardware. So now it's a hardware software partitioning problem. And now of course you have also the problem of control. How does the processor actually manage? How does it initiate the accelerator computation? How does it wait for interrupts, or is there some other way by which it checks whether the accelerator has finished computation, and so on. And everything that we talked about, all the optimization techniques that we discussed earlier, can be applied in order to get better accelerator architectures. An example of this would be something like image processing. This is a very good example for when you might want to use an accelerator in reality, right? Because a typical image processing pipeline has a number of different computations, including pre-processing, color conversion, filtering, feature extraction, right, where features would essentially be, are there any edges in the image, right, are there any key points? Key points would be something like, for a face recognition problem, the locations of the eyes, the nose, the lips, all of those would be key points that need to be identified, and there are standard algorithms that can help to identify such things, right. Analysis, it could be something like, when an image is seen, what is the content of the image? Is there a bicycle in the image? Is there a dog in the image? And what should be done accordingly when you see certain kinds of patterns in the image, right? Now when you want to implement something like this on an FPGA SoC, you need to decide on what your hardware software partitioning is going to look like, right? Typically what happens is, the complex algorithms and the control flow, meaning that when you have something which says, okay, now depending on a certain input or depending on a certain data, I need to have a different kind of behavior, those are well suited to CPUs, because CPUs can very easily sort of make conditional decisions, right? Whereas FPGA, the parallel fabric, the programmable logic that's present on the FPGA is best suited for highly parallel kind of computations, right? When you have a lot of pixels that need to be processed using the same kind of operations, that's an ideal scenario for running it on parallel digital hardware. Filtering, right, is a good example of something like this, where basically you need to apply a similar kind of multiply and add operation on a large number of different pixel values. Now, in order for something like this to work, you also need to have an efficient memory architecture, because just if both the FPGA as well as the CPU are trying to read everything from main memory, that becomes your bottleneck. But given the fact that FPGA fabric typically tends to have certain block RAMs and so on, but may not be big enough to store an entire image, you need to make clever use of what are called line buffers or pixel caches in order to get only the pixels that you need, store them inside the FPGA fabric, perform the computation, then discard them and fetch new data later, right? Now, all of this ultimately, you can look at a high level, we can sort of straight away assume that a pure software implementation would be very flexible. You can modify it easily by just recompiling your code, but it's going to be slow. Hardware accelerated approaches can easily give you 10 to even 100 times speed up for a couple of different reasons. One is of course the parallelism. The second is they are also, once they take the data in, they can hold the data for a certain amount of time and perform a number of computations before going and fetching them again. Once again, the memory can become the bottleneck, and you can break that bottleneck by temporarily storing things in hardware by itself. Of course, the point of an FPGA SoC design is that you want a hybrid approach ideally, right? You want to balance between the flexibility as well as the performance, and this is the freedom that it gives you in the first place. Now, what can you expect as future trends over here, right? Typically what we are seeing now at least is an increasing move towards heterogeneous computing, right? As already mentioned in the SoC discussion, SoCs by themselves tend to have GPUs, AI accelerators, so-called NPUs, neural processing units, image processing units, right? Various kinds of things that are already integrated into them. And domain specific architectures, for example, when you have something like, let's say, a 5G communication system, or even the modems that are present inside modern phones, right, are sort of specialized towards certain kinds of communication algorithms. There could be other domain specific architectures, perhaps things which are very good at solving certain kinds of optimization problems, right. So each of these is sort of increasingly an area of research, and what are the right kind of domain specific architectures to include into a system is essentially something that people are considering. This is where the FPGA SoC is particularly powerful, because you don't have to sort of commit ahead of time and say that this is the architecture that I want. You actually get to sort of reprogram it at as and when you find that you have a better architecture that you have designed. Modern SoCs use so-called chiplet based designs, right? This is something that you might have heard of, especially in the context of things like the newer chips from AMD and various other systems. The idea is that it actually allows you to go down to the silicon level and actually improve the ways in which you are able to integrate things onto a single silicon die, right? Not directly related to the notion of how we design digital systems, but important to keep in mind in terms of how you can actually use larger and more complex digital systems moving forward. One very interesting topic that I would suggest all of you at least explore on your own is the increasing prevalence of so-called open source hardware, right? There are a number of RISC-V processors gaining traction, and there are a number of open source FPGA tool chains that are emerging, and it's definitely a good idea to sort of explore these and understand more about them. But one important thing to sort of keep in mind at the end of the day is digital system design. You should always think of it as a tool. It's a means to an end. Very rarely are you designing a circuit just for the fun of it. You are designing a circuit to solve a problem. Now, where do those problems come from? For that, you need to know the applications, right? You need to know your application domains. AI, ML is of course a very big domain right now, right? But there are a number of others: automotive applications, industrial automation, wireless communication, right, space and defense systems, critical safety critical systems, all of these are different domains that impose different kinds of restrictions or requirements on the kind of digital designs that you do. So in terms of understanding where to go, in future with digital design, having a good background knowledge of applications is a very important and crucial thing to keep in mind.